Okay, hello everyone, thanks for joining. My name is Stuart Millar and I'm presenting this paper called DANdroid, a multi-view discriminative adversarial network for obfuscated Android malware detection. This is a deep learning based Android malware detector that classifies both obfuscated and unobfuscated apps as either malicious or benign, and I'm going to show you that it is effective against a selection of real-world obfuscation techniques. As a quick introduction, there are 82 billion Android apps and games downloaded every year, so automated detection methods are essential. And traditional machine learning involves feature engineering, where an expert analyst uses statistical ranking and selection to turn raw features into handcrafted features. But that's expensive. And this is where deep learning may have an advantage, as knowledge can be encapsulated inside a model instead of providing it by hand. And lastly, malware authors use obfuscation techniques like encryption, reflection, and reference renaming to try and trick a detector into classifying malicious apps as benign. Our approach then, firstly, a deep learning discriminative adversarial network, or DAN for short in DANdroid, with two cost functions, one to minimize classification error for malware, and the others to maximize classification error for obfuscation, meaning that features learned are ignorant, shall we say, of obfuscation. Secondly, multi-view deep learning, meaning more than one raw input feature set using opcodes, permissions and API calls. And thirdly, data augmentation. We augment the original apps in our data set with obfuscated versions of the same apps. So starting with the raw input features then, to get these, there are open source tools to reverse the Android apps. For the opcodes, we use APKtool and \smally to produce .smally files. There are one per Java class, and these are parsed for the opcodes as per Android documentation. For permissions, each app has an XML file with the Android permissions and app requests. This can be parsed too. And for API calls, we again parse the smally files with a tool that uses regex. So what is data augmentation? Well, in deep learning for computer vision, data sets are augmented by adding noise to pixels, changing brightness, rotating the images, etc. And we do similar by taking the original apps and obfuscating them in different ways. The original benchmark data set we used was Ziming, which has 5,560 malware apps. We add 5,920 benign apps to that, and then using a real-world enterprise tool called Dex Protector, we obfuscate all those apps in 4 different ways. Class encryption, API calls obfuscation, string encryption, and resource encryption, plus we make another version with all 4 techniques applied together, and this combination makes detection even more difficult. The overall data set is as follows. You can see they are well balanced, and each app is labeled malware or benign and obfuscated or unobfuscated. It's standard practice to split the data into a training set, a validation set, and a test set. So we use 80% for training, 10% for validation, and 10% for test, with an even balance between malware and benign, and also obfuscated and unobfuscated. We also ensure the original version of an app and any obfuscated version of the same app only appear in one split, so those used to train the model are not used to test it. Otherwise, this can artificially inflate performance. So this is an overview of our model. Full details are in the paper, but you can see on the left the 3 input feature sets: opcodes, permissions, and APIs. The opcodes are input into a convolutional neural network, or CNN for short. This CNN learns patterns in the opcode sequence to discriminate between malware and benign apps. And as I've said, that means these concepts are learned directly and encapsulated inside the CNN instead of handcrafting malicious and benign features externally. The permissions are input to a standard neural net. This learns the relationships between those permissions for malware classification, and the APIs are input to a neural net too. These 3 views are the multi-view. The outputs are concatenated in the center, and forwarded into two different classifiers. This is the DAN part of the network. The first classifier predicts if an app is malware or benign, and the second predicts obfuscated or unobfuscated. This network and others like it contain thousands of parameters, also known as weights, which do exactly that. They capture the weighting of each feature and its contribution towards malware detection. To train this model, each app in the training set is forwarded, the loss is calculated, backpropagated, and the weights are updated. The loss can be thought of as the difference between the classifier prediction and the ground truth. And this forward and back is repeated over and over. And the objective normally is to minimize the loss so the difference between the prediction and ground truth is close to zero. In other words, they match, so our model is making correct classifications. The aim of the DAN is to ensure features learned are not biased by obfuscation. To achieve this, we have two classifiers or discriminators, such that one learns to detect malware and the other ensures ignorance to obfuscation. For malware learning, we minimize the loss as normal, but we want to prevent the network learning anything about obfuscation. Ignore it, to make it resilient to it. So we have our own bespoke cost function that maximizes the obfuscation loss, pushing the obfuscation prediction and ground truth further apart. This reversal or negation of this obfuscation loss is a key novelty. Okay, moving on to our results then. First, we evaluate a single view model trained with only unobfuscated apps to give us our baselines. This single view model is just the opcode CNN. And for training, we use the training set of the original unobfuscated dataset. And the model is tested against the test set of that original unobfuscated dataset plus the test set of each obfuscation type. From this table 1, it can be seen performance metrics worsen with obfuscation complexity. The F1 is 0.976 for no obfuscation, but it decreases radically as obfuscation becomes more complex. But we expect this because the model wasn't trained on obfuscated samples. Next, the single view model is extended to multi-view with opcodes, permissions, and APIs as input. Obfuscated apps are introduced into training 2, so we are training with both obfuscated and unobfuscated apps. And using the unobfuscated benign apps is key. If there were only obfuscated malware apps, then good results could be obtained by classifying any obfuscated app as malware. And we use the same test sets as the previous experiment. From this table 2, it can be seen the multi-view model with the extra feature sets improves malware detection across all metrics compared to the baseline in table 1. However, we need to ensure the model is not silently learning obfuscation characteristics. We want a malware detector, not an obfuscation detector. And this is mitigated in our next experiment, where we introduce the DAN. Here we use the multi-view model and use DAN with two cost functions. One for malware as normal and the other negating the cost for obfuscation. And this allows us to verify the obfuscation resilience of the learned malware features and check if detection performance is affected. From table 3, it can be seen excellent detection performance is maintained, and we can tell the DAN is effective when we look at this confusion matrix, where every single app is classified as unobfuscated. The DAN is not about improving detection performance as such, but removes bias to obfuscation. Therefore, we can conclude our multi-view DAN model is resilient to these 4 obfuscation techniques. With regards to a state-of-the-art comparison, there's very little other research thoroughly testing malware detectors against obfuscated apps. But this table is our state-of-the-art comparison from the paper. What we can say is that we match the state-of-the-art performance of the DANdroid detector without the handcrafting of manual features, which they undertake. And the other methods either don't use enterprise-grade obfuscation or they don't use obfuscated benign apps. So there's the potential for these other malware detectors to actually be detecting obfuscation rather than malware. Some further analysis then. This is a comparison with commercial anti-malware detectors. The authors of 26 here kindly provided us with their PRAGuard dataset. These apps are different to ours and are obfuscated using a different obfuscation tool. And in their paper, they tested commercial detectors from AVG, Norton, and Kaspersky. Table 6 shows the median detection rate for each type of obfuscation and also DANdroid performance. And it can be seen DANdroid achieves superior performance in every case. And we believe this is because our static analysis of an app is much more informative compared to the signatures that these engines use. And this is further proof to verify the features that DANdroid has learnt are obfuscation resilient, whereby each test set app is forwarded through the model with Dan and the model without Dan, and all the feature representations are collected. So we can train 4 SVMs, support vector machines, 2 to detect malware, and another 2 to detect obfuscation. Each SVM is trained with either the features from the network with Dan or the network without Dan. We can see in Table 7 the features extracted from both DANdroid and the network without Dan are very useful for malware detection. As per the accuracy column, they are the first 2 rows. However, we then see that for the obfuscation SVMs, the features from the model that doesn't use Dan contain lots of information about obfuscation because the accuracy is 0.823. However, the features from the Dan model have very little information about obfuscation. And given the major difference in accuracy, we conclude the malware features in DANdroid are of little value in detecting obfuscation. Thus, the learning process is robust and exhibits obfuscation resilience. Finally, our conclusions then, and this is the last slide. DANdroid is a novel deep learning approach that performs strongly in detecting obfuscated and unobfuscated Android malware. Using this multi-view Dan architecture removes obfuscation bias from the learning process via negation of the obfuscation cost in a bespoke adversarial cost function. And DANdroid outperforms 13 commercial anti-malware engines on the PRAGuard dataset. And that's the end of the presentation. Thank you, and I look forward to your questions.